Hi, it's Mr. Rikyo, and today we're going to talk about A1.1 water in the biology syllabus. This is the first topic that we're going to cover in the unit of molecules, of organic molecules and biological molecules. So today's objective is to analyze the chemical structure of water and its applications to biology. All right, I'm going to introduce first the chemical structure and then later the properties that we observe in biology. All right. So A1.1 water, let's go. Um, Before we start, just recalling from your memory that water is made of two atoms of hydrogen and one atom of oxygen, and water is absolutely essential for all life processes. There's no life, or there's no life process that happens without water. Okay. As I said, water has always been essential to life, so it's impossible to imagine life as we know on our planet without water. So life was originated in water environments, in aquatic environments, and until today happens inside water. Mister, we have a plant here or we have an animal. This animal is outside of the water. It's not inside like this fish. Doesn't matter. What we call life is a series of incredible processes that happen inside the cell, and the cell is made of the cytoplasm that has water. So these processes, they're happening on water. Okay. So first of all, the chemical structure of these molecules. We have two atoms of hydrogen and one atom of oxygen, as we saw. And the oxygen is especially powerful in oxidation, in attracting the electrons towards its core. So you end up having an oxygen that brings more electrons, more electronegativity towards its center. So it becomes more negative. And the proton, the hydrogen, becomes more positive. So we call a region or polarity that is more electronegative with more electronegativity, and a region more electropositive or more positive, positive and negative, right? These are charges. These are components of charge. And when you combine two molecules with very distinct polarities, charges, they end up attracting each other. The opposites end up attracting each other. So the oxygen in one molecule will will get closer to protons in the next molecule. So you make what we call hydrogen bonds. These hydrogen bonds are attractions, strong attractions between two water molecules. Okay, and this is very different from covalent bonds. Remember from chemistry. In covalent bonds, you have a share of electrons. Electrons are being shared and are being connected and are being linked between these two atoms. Okay, the hydrogen bonds are what make water liquid or solid. So when you look to the Amazon River, your bottle of water, or the Pacific Ocean, you are seeing trillions and trillions of water molecules combined with by hydrogen bonds, making up an ocean, for example. Okay, this is a very important feature of water molecules, and we're going to see many times. So again, we have an unequal distribution and an equal sharing of electrons. We see here that the oxygen has more electrons or has these electrons closer to the region, to this cloudy region of the atom. And the hydrogen is more positive, on the other hand. Okay, it's very simple, this model. So again, once you check the cloud of charges in the oxygen, you have a more negative region in the oxygen and more positive in the hydrogen. Okay, this is how they interact to make the bonds and to make the attractions, not only with all the water molecules, but also with all sorts of chemicals that are polar. For example, carbohydrates, for example, ions, or some types of amino acids, and so on and on. Okay. Just to differentiate once again, we have covalent bonds that are the share of electrons. These bonds you don't break up. In theory, you don't break up. We have some processes that destroy them, but you don't break covalent bonds. But hydrogen bonds are pretty easy to destroy, to erase, basically boiling water. When you boil water, you are destroying these bonds and making water a gas. So we are dissolving this. Okay, so now let's talk about the properties of water. The first one, it's very important, especially for plants, but also for animals, but especially for plants, is cohesion. So cohesion and its consequences. Cohesion is the transport of water through tiny vessels, through tiny tubes. So one molecule is attracting the other, and they're linked. And when they move through transpiration, evapotranspiration, they bring one another. So when you look at a trunk of a tree, okay, or the stem, you're going to see millions of these water molecules climbing up, moving up to be evaporated in the leaf, okay, through the xylem. But these water molecules are moving through cohesion, through the hydrogen bonds, okay, because they're all linked. And plants, well, plants dominate the planet, so they don't waste energy. They don't use energy to make this movement. It's simply by cohesion and transpiration that is happening on the top of the stem or the tree. So this is the first property. Okay. Also, adhesion. Adhesion is another property. Is how water interact with other materials and dissolve other materials and interact with surfaces. For example, in the bloodstream, in the capillaries, in the arteries. Okay, and also as a way of transport nutrients, oxygen, gases that are dissolved. And other properties, capillary action. So capillary action is when you see narrow tubes, how you form this C-like structure. Okay, that is this property of water to move through cohesion and adhesion. Okay, then we have water as a medium for metabolism. So the major part of molecules and major part of chemicals that we have inside cells, they are water, philic. So they have association. They associate with water. They dissolve in water. Okay, so then life goes on inside these water medium. Okay, of course we have hydrophobic, so molecules that repel water, but the major part of them in cells, they are hydrophilic, not hydrophobic. One example of a hydrophobic chemical is the fats, the oils. Okay, of course we have them, but they're not the majority chemicals. Okay, solvation is also another property. So when you have a bunch of water molecules, if you have a crystal of salt, okay, once water access this crystal, it's going to interact with the charges in these ions, okay, breaking these ionic bonds, okay, and surrounding these atoms by the different charges and attracting the different charges, and then eventually disappearing. This is what happens when you put sodium chloride on water. You disappear the salt because it's being dissolved, and then the waters are surrounding these atoms and these hydration shells. Okay. Then before we finish, we have the physical properties of water. First one, buoyancy. So if something has more density, is more dense than water, it's going to sink. The opposite is going to float. Viscosity. Okay, so a very viscous fluid like honey is one example of this physical property. Water, on the other hand, is not very viscous. It's very fluid. So things happen, okay, in this dynamic fluid that's not viscous, that is water. Next one is conductivity, the possibility of transferring heat, and the heat capacity. In this case, water has a very high heat capacity. So it takes a lot of energy, takes a lot of uh, calories or joules to heat water. Okay, good. These are the chemical and physical properties of water. All right. And of course, many animals, birds, mammals, and all sorts of animals manage these properties and evolved with these properties to adapt and to prosper and to thrive in several environments. Okay, like buoyancy, like thermal conductivity, and so on and on. Okay. All right. This is what we said so far is the 11 higher level. Now, higher level. Okay, so just covering the higher level, additional higher level of A1.1 in water. So basically the higher level of water talks about the origin of water in our planet. Okay, so we believe that one hypothesis for the origin of water in our planet is that water came through several asteroids that hit our planet billions of years ago and these water that came in form of ice or other components stayed here, okay? Stayed here for gravity, and as the Earth began to cool down, this water was able to become liquid and condense, and eventually being retained and forming the oceans that we have, okay? So why do we have this hypothesis of extraplanetary origin of water? Because water is a pretty common chemical in the universe, although it's essential for us, and although it's valuable for us, it's not something very unusual in the galaxies, in the universe out there. Okay, so this is a very plausible hypothesis for the origin of water. And as we see, as we observe water in our planet always being surrounded by life, and life was originated on water, we and astrobiologists, special astrobiologists, they end up trying to find life elsewhere in other planets by searching for traces of water. But this is a hint. This is useful. This is interesting. But it's not a rule. Okay, if life exists in another planet or in another galaxy, maybe we can have a completely different framework or system. Um, and that's it. And finally, we have what we call the habitable zone. That is where our planet is located in. So once we received this water, once this water condensed and became the oceans, our planet is in a zone that's called habitable zone. So it's not too hot and it's not too cold, and it's adequate for the liquid water and prosperity of life. And this is what we see in our planet, an incredible diversity of life forms. That's it for today. This is the additional higher level. Well, we also cover the center level, and I hope that was helpful.